Okay, good morning. So this is the last topic I want to talk about permutations, but before doing that, the reason I want to talk about this because I see it in the problems in the book, okay? So it is better to have an idea what is the meaning of cyclic permutations. For example, how many ways six people can sit in a round table. Okay, something like that is in the book. But before doing that, I would write some warm-up problems so that see that how you solve the problems from the previous lessons and give you time to think about it. We discuss about them and then start the new lesson, okay? So let me write them down here for you. So how many permutations of the numbers one, two, up to 9 are there such that no pair of the numbers 1, 2, and 3 are adjacent. So that is one problem. The other one, let me write this. How many 12 permutations of the letters of the 26 English alphabet are there as such that each permutation contains all the letters A, B, C, and D, but no pair of these letters are adjacent. Okay, so you can work a little bit on these two problems. Oh, okay, and let me also add one more. Number 3. So consider the word yes, this mag. Yes. And then say how many 4-letter words can we write using the letters in this word? Okay, so you can think about them a little bit. and then we do it together, and then we start a new lesson.
Pair is adjacent. Do you mean simply that the letters and numbers aren't adjacent to each other?
So which one here?
Yes, both.
So it means you have three numbers, 1, 2, and 3. No pair of these three numbers, say 1, 2, 1, 3, 2, 3, none of them are adjacent.
Oh.
Yes. So 1, 2 are not adjacent, 1, 3 are not adjacent, 2 and 3 are not adjacent.
Okay.
Yes, that's the meaning of that, if my English is not perfect. Okay, should we start solving them? So let us see how it goes, yes? So how many permutations of the numbers 1, 2 up to 9 are there such that no pair of the numbers 1, 2, and 3 are adjacent? So how should we solve the problem? Any ideas? Yes?
First, we assign spaces for the non-problematic.
Yeah, exactly. That is a standard model we had so far. So I just want to review. So we have 9 objects, 1, 2, 3 up to 9. Here, objects are numbers. And then I don't want to have any pair of these adjacent. So we actually arrange the non-problematic ones. The non-problematic ones are which numbers? 1, 2, 3 up to, non-problematic ones start from 4. Yes, so 4, 5, 6, up to, I can write all of them, 4, 5, 6, 7, 8, 9, yes? These are the non-problematic ones. So I arrange them first, yes? So how many locations I need for them? 6. So I need 6 locations. 1, 2, 3, 4, 5, 6, yes? So which model is useful here? I have 6 distinct boxes, and I also have 6 distinct objects. I want to arrange them. So that is the factorial model, yes? So this becomes simply 9 factorial. So I have 9, so let me write stage 1. So stage 1 is arranging non-problematic numbers in these locations. So it becomes, the number of them is 6 factorial. Okay, but what was the method we discussed so far? When you put them here, then they will open up some spaces so that I can use 3 of them to put the problematic numbers there. Yes? Is that right? So when I put those problematic numbers in these boxes, none of them will be adjacent because at least there is one element between them. But now, which model is working here? Objects that I have are 3 problematic objects, 1, 2, and 3. But how many boxes I have? I have 7 boxes, these blue ones. So I have 3 marbles distinct, and I have 7 boxes distinct. I want to distribute the marbles in the boxes so that each box receives at most 1. Yes, and that's exactly the model we discussed. So this is important. Let me repeat this again. So if you have n marbles distinct, but you have less number of boxes, again distinct, let us say r. I assume that r is less than or equal to n. So I have n marbles distinct, r boxes distinct. I want to put these marbles in the boxes in a way that each box receives exactly 1 marble. The number of ways that I can do it is Pn and r. Yes? On the other hand, if my marbles are r, the number of marbles are r, the number of boxes is n. Again, r is less than n. This time it means that the number of marbles is less than the number of boxes. I want to distribute them here. I cannot say that every box should receive exactly 1 marble because we do not have enough marbles. But I can say that each box is supposed to receive at most 1 marble. That model the answer in how many ways I can distribute this again is the same number. So you have to have, we discussed about why, so I don't explain again one. If you have forgotten, you can watch back the videos. But the point is that you have to have these two models. And if the number of marbles and the number of boxes are exactly the same, this model will be n factorial model, yes? So here, 6 factorial for distinct objects, distinct boxes, the black ones. So this is the factorial model. But then I have 7 boxes, but I have only 3 marbles. Marbles are distinct, boxes are also distinct. So which model is that? This is this model that I have less number of marbles than boxes. So the number of ways, stage 2, is arranging the problematic ones in the blue boxes. In how many ways I can do that? The answer is P, okay? N and R. N is always the number, bigger number. Here I have 7 boxes, 3 marbles. So I have to write 7 first, 3 second. Yes? And then what is the answer to the whole problem then? To achieve the goal, I cannot just do a stage 1 and leave it. I cannot just do a stage 2. I have to do one after the other. So whenever this happens, I have to use the product rule. So this is simply 6 factorial multiplied by P, 7, 3, and it's enough here. If I insist you give me the answer, probably I will provide you with a calculator so you can calculate this number. That is enough here. Is that clear? Okay, so this is important. This abstract model, you should have it in your head so that you can compare. Okay, let us go to the next question. In how many 12 permutations of the letters of 26 English alphabet are there such that, so how many are there such that each permutation contains all the letters A, B, C, and D, but no pair of these letters are adjacent? So first of all, I hope that you remember, so what is the meaning of 12 permutations? Because in English we have 26 alphabets, letters, and then I don't want to use all of them. 12 permutation tells you that you have to choose 12 of them, but there is a constraint that you don't have freedom in choosing A, B, and C, and D. You have to choose them, okay? So you have only freedom about 8 of them. Okay, so how do you solve this problem? So I want to choose 12 letters, 4 of them have to be these letters. Another constraint is that those letters shouldn't be adjacent. No pair of them should be adjacent. So you have to be able to analyze the problem according to the models that we have. Any ideas?
You arrange the non-problematic letters.
Yeah, exactly. So this is, I just want to tell you that the reason that you know that everything here that I'm talking about is 1.5 page in the book, but I'm talking about it 5 lessons or more. That's because these problems are in the texts, in the problems. So if you don't have these models, coming up with these models without helping the teacher helping you is not that reasonable. That's why we went through these problems, because these are standard model problems that you should have in mind so that you can compare and use them suitable in the problem. Okay, so what do you say here? So we know that I have to have so okay, tell me what to do. What is your first stage? So in total I need 12 letters, but 4 of them are A, B, and C, and D. So 8 of them are left. So what do I do?
P of 8 and P of 24 and 8.
Yes, because it means that I don't have any choice for A, B, C, and D, so they have to be there. So there are how many more letters for me? 22. From those 22, I have to choose how many? How many?
8.
8, because in total I want to have 12. A, B, C, and D are 4 of them, so I have only freedom in choosing 8 of them. But 8 of them out of how many? The leftovers, 22. But then I want to arrange them. Okay, so what do I have? In principle, how many marbles I have, if I want to compare it with this model, by this simple analysis and reading the text, you understand that you have 22 marbles. What are those marbles? All English alphabet except A, B, C, and D. Are they distinct? Yes. So that is the mark. But how many of them I want to choose and arrange? How many? 8. Yes. So I will choose 8 of them. So I put 8 boxes here. 1, 2, 3, 4, 5, 6, 7, 8. I need 8 locations. So I will choose 8 of them and arrange them in this box so that every box receives exactly 1 marble. That is this. Which model is that? The upper one or the lower one? The upper one, because the number of marbles is more than the number of boxes. So what I do, I just write the stage 1 is in how many ways it can be done? 8. Yes? Is that right? Okay, now let us say that the stage 1 is done. What does it mean? It means that you did it in one of these ways. For example, I don't know, you choose Z to be here, X here, U here, S here, T here, B here, W here, and O here, for example. This is one of these ways, okay? And now the second stage is to put those 4 letters in a way that no pair is adjacent. And that's exactly this model, this method, yes? So how many empty spaces I have? 1, 2, 3, 4, 5, 6, 7, 8, and 9. Yes? So how many boxes I have now? I have 9 boxes. But how many marbles I have? Here A, B, C, and D are playing the role of the marbles. So which one of these models is working now? The lower. Yes? But the answer is again the same. Okay, so stage 2, I have P. The number of marbles is how many? 4. The number of boxes is how many? 9. Yes? And then what is the total answer to the problem? What is the final answer to the problem? I have to do these stages one after the other so that the task is accomplished. So this means that I have to multiply. So that's simple. You see, this is a problem. It's a good problem to understand the model because I use both of them in one problem. Yes? So P22 8 times P9 4, and that's it. You can keep the answer like this. What about the last one? Let me also discuss a little bit about this word. Let me tell you what we have so far. So you remember, this is what we have so far. So if I have n distinct objects, and I want to arrange them, and I want to use all of them. So in how many ways I can do that? N factorial. I am emphasizing on the word distinct. So we have a formula for the case that I have n distinct objects and I want to use all of them. Yes? We also have a formula if I have n distinct objects but I don't want to use all of them. I want to use r of them. Yes? All of them. Use all of them. This is the answer. Use r of them. Of course, r is less than n. So we have a formula again. What's the formula? P, n, and r. Yes? Now, let us go back here. I have n not necessarily distinct objects. So n not distinct. Let me write it simple, okay? And I want to use all of them. Do I have a formula again? Do you remember what was the formula? The repetition model formula, yes? Be careful. N distinct, use all of them, n factorial. N not distinct, use all of them, we have a formula. The formula looks like something like this. N factorial divided, I don't know, by n1 factorial, n2 factorial is up to some nk factorial. If I ask you what are these are the number of repetitions of each object. So n distinct, all n factorial. N not distinct, all, we have a formula. N distinct, I want to use r of them, we have a formula. But n distinct, n not distinct, n not distinct, use r of them, no formulas. Yes, so this, if this happens, you have to solve it case by case depending on the problem. Is that clear? So I want to have this picture in mind. This is helpful because so you know, for 3 parts we have formulas. If this is going to happen, that the objects are not distinct, but I don't want to use all of them, I just want to use a collection of them, a sub-collection of them, that there is no formula for it. You have to consider the problem for that problem. Yes? So, I hope that you agree with me. So let us review this in this problem. Consider the word magmac, okay? If I ask you how many 6-letter words can we write, do we have a formula for it? Because magmac consists of 6 objects, not distinct. But if I want to use all 6 of them, I have the formula here. So let us review. Can you tell me how many 6-letter words I can use, I can construct using the letters in the word magmac? You will tell me yes? 6 factorial.
Over 2 factorial.
Why over? Because m is repeating how many times? 2 times. So I have to put a 2 factorial because of 2 repetitions of m, and 2 factorial for repetitions of a's, for example, and 2 factorial for repetitions of g's. But the problem is now what? The problem is with repetition and not using all of them. So that is this question, that is this no formula problem. Yes? So this means that you have to consider it case by case. So it doesn't mean that these models are useless. No, these models, as you will see, are useful. But you have to decompose the problem into different sections and solve it and then add them up. That's what I'm telling you. And that is the reason there is no formula. Because depending on the letter or the permutation, you don't know what are the general cases. We have to consider it case by case. Okay, so I don't know. How do you think about the problem now? So let me write the word magmac here. So we have 2 M's, 2 A's, and 2 G's. And I want to construct a 4-letter a 4-letter word. So I don't know how you think. There is nothing that I can teach you here. You need to think about it yourself. So how you categorize the problem, how you divide the problem. So one way is to say that, is it possible to write a 4-letter without any repetitions at all? No, because I have only 3 different letters. So if I want to write a 4-letter, I have to repeat one. Okay, but then I can categorize it so that I can repeat only 1 letter, yes, or I can repeat a pair of letters, yes, is that right? So this is the only possibility. So repeating 1 pair, for example, M, A, G, G is one of them. For this one, I have also different options. I can write G, A, M, G again, okay? So in any way that I'm saying that here, only 1 letter is repeated. Okay, can you tell me in how many ways I can write a 4-letter word in which 1 letter is repeated? Okay, I decompose this problem into 2 stages. I would say stage 1 is choosing the letter that is supposed to be repeated. Yes? How many options I have? 3. I can say that I choose A to be repeated, or G to be repeated, or M to be repeated. So stage 1 is for that case 3. So now let us say stage 1 is done. It means what? It means that I made my mind about the letter that is supposed to be repeated, and let us assume that that is G. Okay? Okay, so G is repeated. It means A and M are not repeated. So I have this situation, then I want to arrange this. In how many ways I can arrange these letters? Let us say M, A, G, and G. In how many ways I can arrange them? That is the repetition model. I have 4 letters. M and A are not repeated, but G is repeated 2 times. So I divide by 2 factorial. So this means that a stage 1 and a stage 2 have to be done consecutively. So the number is 3 times 4 factorial over 2 factorial. And if I answer this one, 4 factorial is 24, divided by 2 is 12, so that's 36. So if I ask you what is 36, it is consisting this word and all permutations. It is consisting A, G, M, M, and all permutations. It is consisting what? G, M, and A, and all permutations. In total, it is 36. So you have to have a good understanding why this 36 took care of all these cases and their permutations. Is that right? Okay, but this is not the whole story, because I can have another possibility for writing a 4-letter word. And it might happen that I have 2 pairs repeated. Okay, again, I break it into 2 stages. Stage 1, choosing that pair that is supposed to be repeated. And so in how many ways I can choose my pair? 3 again. I can choose pair AA, MM. I can choose pair AA, GG. I can choose pair MM, AA. So first I choose my pair. So in how many ways I can choose my pair? 3 times. 3 ways. Now let us assume that the stage 1 is done. What does it mean? It means that I made my mind about that pair. So let us say that I made my mind to choose AA and MM. Now I want to arrange them. So this is which model? Again, I want to use all of them with repetition. So stage 2 is how many ways? 4 factorial, but divided by what? 2 factorial because of repetitions of A and M. And then what is the answer to this part? Is the multiplication of them. So 3 times 4 factorial over 2 factorial, 2 factorial. 24 divided by 4 is 6, is 18. Okay, if I ask you, so what is 18? 18 consider this and all permutations. It consider AAGG and all permutations. It consider MMGG and all permutations. It is 18. Okay? And then what is the final answer to the problem? What should I do with these 2 numbers, 36 and 18? Yes? Add them, yes? So 36 plus 18. So the answer is 54. Yes? So this is important. I thought, I don't remember exactly, did I bring it up before? But this is good to have it in your notebook so that you can compare which one is which. Because you know that combinatorics is a very diverse subject, and the problems could be extremely hard. So it is better to have some anchors in your mind so that you can invoke them, yes, whenever you need them. Okay, any questions? Okay, finally, the last part of the permutation, which I saw some problems in the book, and it's under the title of cyclic permutation. Yes. So how should we do that? What is the meaning of a cyclic permutation? So let me clean this part. So a cyclic permutation is a permutation. You can arrange the items around a circle, but the exact location of each item is not important to you. the left and right neighbors are important. So as far as the neighbors of none of the arrangements are changed, you consider them the same arrangement. Okay, so it is a little bit convoluted. Okay, so let us say that I have a round table with 4 chairs. So you are looking at the round table from the above. Okay, and then I have 4 people. So let me call them A, B, C, and D. They sometimes ask in how many ways these people can sit around this round table. Okay, so there might be, you say, 4 factorial, and that is not wrong. But this is conventional. When they say that people are sitting around a table, they mean the neighbors are important. For example, if you write A here, B here, C here, D here, and then if you do this way, let me just put the chairs here again. If you put A here, B here, C here, D here, of course you can recognize the difference. Yes, this is different from this setup. And when I say 4 factorial, I consider this one item, I consider this a new item when I say 4 factorial. But in the cyclic permutation, usually this is the convention. They said people are sitting around the table. In how many ways they can do it? They mean this and that should be considered the same combination. Why? Because if I ask A, who is your right-hand neighbor? A will say D, and who is your left-hand neighbor is B. Okay? The same situation happens here. If you ask the same question for this arrangement A, the answers are exactly the same as before. So they want to consider these 2 states, these 2 items the same item. Whenever you want to have this, that is called cyclic permutation, which usually in combinatorial books, they try to convey this idea to you by saying people are sitting around the table or something. Because in principle, you can sit down around the table, but still it might be 4 factorial. For example, let us say this is the president, this is the prime minister job, or it means, and then I don't know, vice president, the Ministry of Defense, or whatever. Of course, it means that it is completely different because now A is president. When you rotate them, then D will be president. So in that case, if I ask you in how many ways people can sit around the table, you will still say 4 factorial. Yes, because the locations are different. So it depends. But usually this is the convention. When say that people are sitting around the table or something like that, a circular table, they are telling you that we want you to consider the cyclic permutation. Okay, so now can you tell me how many cyclic permutations we have? So this one and that one are the same if we want to consider cyclic permutation. Can you tell me another arrangement which is still the same arrangement considering cyclic permutation? What is that, for example? And how many of them are there? Yes? Okay, I wrote two of them for you. As far as this is concerned, cyclic permutation are concerned, this and that are the same arrangements for me. Can you tell me another arrangement which is the same, but it is not as before? Yes?
C on the top,
C on the top,
then D to the right,
D to the right,
A to the bottom,
A,
and then B.
B. Yes, that's correct, because the neighbors, none of the neighbors has changed, yes? Is that right? So in principle, if you start reading from A, either counterclockwise or clockwise, for example, let us go clockwise, how should I read it? A, B, C, D. And when I start from A again and read it in the same direction I read this one, it is still A, B, C, D. And if I start from A and read it in the same direction, it is still A, B, C, D. So they are not different items. We want to consider them the same. That's my goal. Is there any other name for it? Yes, one more. Yes, what is that? So let me draw it here. There's one more. What is that? So I started with A, C, D. I can start with B. Yes? So how should I go? So in this rotation, after BC is coming, if I go clockwise, so after B, C should come, after C, D should come, and then A should come. A, B, C, D. So if I start with the same item and go clockwise, for all of them, they are read the same way. Okay, so this, be careful. When I say 4 factorial, I consider these 4 cases distinct. But if I insist to keep these the same, what will be the answer? Let us say every linear permutation corresponds to every 4 circular, every 4 of them is just now 1. So every 4 of these items, you should consider it 1. So of course, can you tell me something which is really different from these names? Can you tell me an arrangement which is not considered here? So all these 4s, don't count them 4 times, count them only 1 time. Yes? And can you tell me another scenario which is not there? Yes? A on top,
And then C.
C,
And any other letter.
yeah, doesn't matter, B and D. But now, because this is different from that, why? Because if I start with A and go clockwise as before, the way I read it is different. It becomes ACBD. What was the reading here? All of them, it was ABCD. So this is different from them. And how many names I can write for this? 4 again, by those 4 rotations. Okay? So let us assume that you are patient and write all these circles. How many circles you will have at the end? 4 factorial. Yes? But are all these 4 factorials for my case distinct? No. Every 4 of them is now 1 item. So what is the answer to this problem now? 4 factorial divided by 4. That's the answer. So if you have n distinct objects and you want to arrange them in a row, it becomes n factorial. But if you want to arrange them in a circular way in which what I described for you matters, you have to write n factorial but divided by n. Because if I have n items, I have n different ways of rotating. But this can be simplified always. So you can write it as n times n minus 1 factorial divided by n, and this n and that n are gone, so you will get n minus 1 factorial. So if you want, you can use it in the exam or whatever. So if I want to calculate, if I have n distinct objects, and I want to use all of them, yes, in a linear way, then I have n factorial. But if only neighbors matter to me, or I want to arrange them in a circular way, the answer is not n factorial, it's n minus 1 factorial. That was one of the questions in the book, so I want to describe so that you understand. But you can use it, so you don't need to justify it. You can say that I want to use circular model or something like that. Again, then you can write the answer because we derived this once for all, and the answer is n minus 1 factorial. Okay, is that clear? Okay, so now let me ask you this question. Let us say that we have 3 couples, husband and wife. So couple 1, husband, wife 1, husband 2, wife 2, husband 3, wife 3. I think it's also a problem in the book, I don't remember. Okay, let us try to review all the models. These people are supposed to stand in a queue. And how many ways we can do that? 6 factorial. Because they want to stand in a queue, there is no circular arrangement, that's just linear arrangement. And I have 6 distinct objects, I want to use all of them, so that is the factorial model. So it becomes 6 factorial. Let us say that in this queue, every husband and wife, they want to be next to each other. In how many ways I can do that? No, be careful. So husband 1 should be next to wife 1, husband 2 should be next to wife 2, and husband 3 should be next to wife 3. But it's still in a queue line. I'm just reviewing the previous model. Yes?
3 factorial times 2 to the power of 3.
3. Yes, because you say that that's the box model. Yes, I put these people in the box. Then how many objects, how many distinct objects I have? This box and that box and that box are distinct. Yes, because in this box you see these people, in this box you see different people. So these boxes are different. So I start arranging them. So in how many ways I can arrange 3 different boxes in 3 locations? 3, the factorial model is 3 factorial. But now, I didn't say which one should come first in the queue, which one should be second. So this means that these have 2 arrangements. These has 2 arrangements, and these has 2 arrangements. So I have to multiply by 2 factorial, 2 factorial, 2 factorials. That's the answer. This is the number of ways that these people can stand in a queue line in a way that every husband is immediately next to his own wife. Okay. But now, let us solve this problem in this way. Let us say that they want to play a game or whatever. They want to sit around the table. Without any constraints, how many ways I can let these people sit? So I have 6 chairs around them, but it doesn't matter. The location of the chair is not that important for us in a game. Might be it is better to see which one is sitting next to that person. So even if this is not the case, when I tell it is a circular table or a round table, remember that I am telling you consider the cyclic model. Okay, so if without constraint but cyclic model, how many ways I can arrange them? You see 6 people, but don't say 6 factorial, say 5 factorial. Yeah, so that is 5 factorial without any constraints. But let me solve that problem. Instead of queue line, let us say that I want every husband be next to his wife, either on the left or on the right. So how can I solve that problem? Is the question clear? So for example, one of the arrangements that is acceptable to me is H1 here. For example, W1 here, and W2 here, H2 here. This is acceptable, yes? And then let us say this is H3 and W3. This is one of the acceptable arrangements because this wife is sitting next to his husband. But of course, in this case, on the left side, yes? Here, this is also acceptable because this wife is also sitting next to his husband, but of course, in this case, on the right-hand side of the husband. But this is adjacent. So this is one of the arrangements that I want to consider as one item. Okay, for example, let me ask you this question. Do you think that if I draw this scenario, okay. First of all, is it an acceptable arrangement according to my desire? Yes or no? Yes, because still this wife is sitting next to his husband, this wife is sitting next to his husband, and this wife is also sitting next to his husband. So that is an acceptable scenario for me. But is this scenario different from this or not?
It's different.
It is different because I told you, whenever you want to see it is different, start with one of them, for example, H1, and decide to go either clockwise or anti-clockwise. For example, let us decide to go clockwise. How do you read it? It is H1, W1, W2, H2, H3, W3. But go here and start from the same person you started here and go in the same direction that I chose to go here. Okay, is the reading different?
Yes.
Yes. So if the reading becomes different, you have to consider this and this as 2 items, not 1 item. Yeah, is that clear? So this is the problem. Okay, now tell me, how should I solve the problem? Yes?
Can I just say the answer?
Yes?
It's 16.
Yes. But how did you do that? So you use the box scenario. So still we have these boxes. But this time I want to put the boxes around a circular table. So that part is what? Cyclic permutation. Yes? So if I put them in the boxes are distinct, but I want to arrange the boxes here. Okay? So this means that this is not 3 factorial as usual. It is, instead of this, I have 3 1 minus 1 factorial. Okay? But now the boxes are there. So this is box 1, husband 1 and wife 1 is in this box. I don't know, this is box 2, husband 2 and wife 2 are in that box, and this is box 3, husband 3 and wife 3 are in that box. Okay, but now what can I do? In this box, husband can sit here, I mean here and there, for example. So, or the other way around. So I will have a 2 factorial because of the arrangements within that box itself. And then I will have a 2 factorial there, and I have a 2 factorial here. So then instead of having this as an answer, this will be my answer. So the only thing, so what you said is correct, because this is 2 factorial, 2 factorial, 2 factorial, 2 factorial, which is 2, 2, 2, 2, is 16. Yes, something like that. I don't want to push you so much, but I saw this problem in the book, so I want you to know about the circular arrangement, because sometimes it becomes a little bit strange why you have -1 there. Is that understandable? Yes? Okay. So I think we can stop here, and then you can start working on your own. So the topic of permutation is completely finished. A little bit at least. So, but of course, the problems could be sometimes very hard. But I don't think you have harder problems than this. You will not face any harder problem than these problems we have solved so far. But the next topic will be combination. I don't want to start it today. We can start it next time. So combination is a choosing, but in which order does not matter. Only the combination of the members that I choose matter to me. So that is the first time that order does not matter. So when order matters, it is called permutation. When order does not matter, it becomes combination. And that's also a very important part. And then after that, we use the combination problems to understand the Newton's binomial theorem. And that would be the end of this chapter, because the graph is completely eliminated by Schoolwerk. So that would be the end of this chapter. And then we start a completely fresh lesson, which is differential equation, and it is very similar to Math 4 in nature, no discrete mathematics. But of course, differential equation is also very important, and sometimes it might be a little bit hard. But the way that you need to think about it is the way that you need to think about Math 4. So you see, this mindset is completely different from what you had in Math 4. But again, the next chapter will be very the same. Any questions? Okay, so I have updated the Google Classroom. So there are some exercises in the book. I prefer you to start working on them, and if you have questions, please let me know.